This is the second video on Unit 2 Transient Analysis. In the previous video, we saw the working of capacitors and inductors. Now coming to the heading of this unit, Transient Analysis. What is meant by transient response? Transient response is otherwise called as the natural response. It is the way a circuit responds to energy stored in storage elements such as capacitors and inductors. Or in another way, it is the working of capacitors and inductors in the absence of any external source. If you look at the given example, you can see here a switch which can be in position A or B. If the switch is in position A, the circuit is completed through a battery, a resistance and a capacitor. Once the capacitor is fully charged, the switch can be thrown to position B. Now what happens? The energy stored in the capacitor discharges slowly through the resistor. So this behavior, the working of a capacitor in the absence of an external source, is called as the transient response. And the analysis of this transient response is the main topic of this unit. If you look at the main content of this chapter, we already discussed capacitors and inductors. So the topic now is source-free RL and RC circuit. In other words, that is the discussion of transient response of RL and RC. So first we will look at a source-free RC circuit. So this is the circuit as a result of disconnecting the source. We have only one capacitor and a resistor. So you can see here there is a current flowing through the capacitor and the resistor. This is actually due to the energy stored in the capacitor when the battery was initially connected. So looking at the circuit and applying KCL at the junction, we can write IC plus IR is equal to 0, where IC is the current flowing through the capacitor and IR that through the resistor. Now IR, all of you are familiar with the Ohm's law, can be written as V over R, and the expression for IC can be written as C dV over dt, where V is the voltage across the capacitor. Now this is a differential equation. Simplifying the equation for an expression for the voltage related to the time, or voltage as a function of time, the equation can be derived in this form: Vt is equal to V0 exponential minus t over Rc. Let's be familiar with the terms that we have in this equation. Vt, of course, that is a voltage at or across the capacitor at any time, that is, it's a function of time, is equal to V0. V0 denotes the initial voltage or the maximum voltage with which the capacitor was charged, exponential minus t over Rc. Now this term explains the nature of that discharging curve, or the capacitor discharges exponentially. This exponential curve is otherwise called as the natural response of an RC circuit. The natural response of the circuit is the behavior of the circuit itself with no external sources of excitation. So if you look at that equation and nature of the exponential curve, you can see the exponential curve in this graph. Let us now define a term which is called as the time constant τ. It is nothing but the two constants of the circuit, R and C. Now there is a significant importance to this term called tau, or time constant. It is actually responsible for the shape of the curve, how deep the exponential curve is, As you can see here, as the value of tau increases, the curve decays more slowly. That is, as the value of tau is more, the capacitor takes more time to discharge and becomes 0. The time constant of the circuit is defined as, it is the time, of course, for the response, that is the output, to decay by a factor of 1 by E, 36.8% of its initial value. If you look at the graph, tau is the time at which the voltage is 0.368 of its initial value. And from this graph, it is clear the voltage decays faster if the value of tau is smaller. Okay, so with this knowledge, now we can summarize. In order to do the analysis of a source-free RC circuit, we need to have the following details. 1. The initial voltage across the capacitor, that is assumed to be the maximum voltage with which the capacitor was initially charged. The second information required is the time constant, which is equal to RC, because that is responsible for the decay curve, the exponential decay curve. So if you know these two information, that is V0 and the value of tau, we can calculate the voltage across the capacitor at any specific time. Okay, now going to source-free RL circuit. Much similar idea can be used for the analysis of source-free RL circuit as well. So having a look at the circuit, this is a circuit which is the result of disconnecting from an external source. That means in the absence of an external source. Now going with the mathematical treatment by using KVL. So remember, for an RL circuit we are starting the equations, the derivation by KVL equation. So KVL, the sum of algebraic voltages in a closed loop is equal to 0. So here you can see two voltages VL and VR. So VL plus VR is equal to 0. VL is the voltage across the inductance, which is represented as L di over dt. VR is the voltage across the resistor, which is IR. By using similar techniques of simplifying the equation, an expression for an instantaneous current can be derived, which is equal to I0 exponential minus RT over L. So let's once again be familiar with the terms that we have here. IT is the current flowing through the circuit at any instant of time. I0 is the initial current. Exponential, so here again you have an exponential term. That means the behavior of an RL circuit also is an exponential curve. Exponential minus RT over L. R is the resistor value, L is the inductance value. So in the circuit as well, we have the term called the time constant. This time the expression for the time constant is different. Of course, in terms of L and R, tau is equal to L over R. And with that substitution, if you look at the equation for current, it is now in a similar format as that of voltage across a capacitor. Only thing is, the value of tau is different, and this is for a current equation and that was for a voltage equation. So this is the exponential decay curve for the current through the circuit of an RL circuit. So tau is defined as, here again, the time required for the response to reach 36.8% of the maximum value. So the general form for current in an RL circuit is much similar to that of voltage in an RC circuit. So when we do the analysis of a source-free RL circuit, there are two key parameters, that is I0, the initial current through the inductor, and the second parameter is tau, which is equal to L over R. With these two parameters, we can find out the behavior of an RL circuit at any instant of time. So after the discussion of the two topics, source-free RL circuit and source-free RC circuit, here is a comparison or the summary. So the first topic that we saw was an RC source-free circuit. So it was the voltage which was decaying or discharging. Remember, a capacitor, a fully charged capacitor will always discharge. The voltage discharges slowly, and the expression for the voltage at any instant of time is represented by an exponential curve. A similar case is for an RL circuit, but this time it is the current which decays, but the nature of the curve is much similar. It is an exponential curve too. So the equation, the transient response curve for both an RL circuit and an RC circuit are exponential. The equations are much similar with two main differences. RL circuit, it is the current response, and in RC circuit it is the voltage. Another difference is the time constant is L over R in an RL circuit, it is RC in a RC circuit.